All right, class, this is 8.7, 8.8. I think I can do this all on the same screencast. So let's get into exceptions to the octet rule. So the two things we're going to be talking about are exceptions to the octet rule and covalent bond strength. There are three types of ions and molecules that do not follow the octet rule. So there are ions or molecules like the whole molecule has an odd number of electrons, which means one of them has to be what we call free radical, where it has to be single by itself. And there are some situations where the molecules are stable, relatively stable that way, although it doesn't happen often. So this would be something that I would consider to be, that would be considered rare for me. So we won't see that too often, and I don't think we even get a chance to take a look at an example here, which is fine. Ions or molecules with less than an octet. I'm going to show you BF3 and why it's important that that one has less than an octet. Ions or molecules with more than an octet. So we have odd number of electrons, smaller than an octet or larger than an octet, and those larger than an octet are called expanded octets. And I'll show you what that means by expanded octets. So the first one is odd number of electrons. There are some nitrogen and oxygen compounds. I think NO actually is one of them because nitrogen has 5 and oxygen has 6. So that means somewhere there's got to be nope, that's not it. We might end up with just single and a single. Actually, it's just one, so it would be like this. That would be it like that with oxygen. There we go. And we have our single electron. That would be an example of just NO, of having an odd number of electrons. So let's move on from there. How about BF3? So BF3 it makes sense that boron has 3 valence electrons, and then because it has 3 valence electrons, each one like bonds with the fluorine single electron. So we end up, now look what they've done here. They've made this more complicated than it needs to be. And the reason why I say that is because boron looks like this. And then if you think that each, like if you understand that each fluorine looks like this, then it seems to fit that you can just bond each fluorine with the single electron from boron to look like this. So they go through this whole like double bond from fluorine, which does not happen, or at least is not a stable form for fluorine. And then you end up, these plus ones and minus ones, this is all formal charges, and the formal charges, if you remember, are valence electrons. Boy, I'm not writing that very well. Valence electrons minus assigned electrons, and we'll just act like that's an acceptable way to shorten assigned. And then, so it says, giving boron the filled octet places a negative charge on the boron and a positive charge on the fluorine. This is the problem. There is no positive charge for fluorine. Fluorine is the highest in electronegativity, which means it always wants to have the negative charge. So this is not a viable option or some option that is accurate. So instead, we say this one is the one that makes the most sense, and these are much less stable. So that's where we are. It makes sense that that's the most obvious one. The only problem is that each one of these lines is worth 2 electrons, so that's 2, 4, 6. Boron has 6 electrons instead of 8, and boron is happy with that because it's less than 8, but the rest of the molecule is more stable because of it. So the octet rule, there are exceptions to the octet rule, and this is one of them. This is a relatively common one. We see this with BF3, and we also see it with BCl3. The other ones we don't see too often. So that's fewer than 8 electrons. Okay, so it says filling in the octet for a central atom results in a negative charge on the central atom and a positive charge on the more electronegative outer atom. Then the central atom doesn't get the octet then. It just gets less of an octet. That's what the lesson is. That's what the point is. So how about more than 8 electrons? So if you remember, phosphorus has a dot diagram that looks like this. It looks very similar to nitrogen's, where we have a situation where I have 3 single electrons, and then here I have a pair of what we call lone pair electrons. Well, sometimes phosphorus will do this instead. Each one of those 5 electrons will form its like own bond, like this. And we see it happen here with PCl5. So PCl5 is what we're looking at here, and this actually makes sense. So PCl5 can happen, and it's because phosphorus is in the 3rd row of the periodic table. So this can happen for the 3rd row. So you would never see NCl5, even though nitrogen is in the same group. It has 5 valence electrons. Nitrogen only makes 3 bonds because it's not in the 3rd period of the periodic table or below. So this always happens, but not that. Okay, that does not happen for nitrogen. Only phosphorus and below phosphorus, meaning arsenic. Where else are we at? Antimony, bismuth, although bismuth is metal and tends to give up electrons. All right, so let's keep moving here. So even though we can draw a Lewis structure for the phosphate ion, phosphate, if you remember, is PO4 with a -3 charge. Whenever we draw a polyatomic ion that has a negative charge, we always put it in brackets. This is something we're going to learn to do when we practice more writing polyatomic ions. So here's what happens. So if I take a look at this, I get my formal charge of -1, -1, -1, -1, and +1, and that still equals out a -3 for the charge of the ion, the polyatomic ion. Over here, though, I get a 0 and a 0, and for formal charges, if you have to choose between the 2 structures, the one that has the 0 and the 0, instead of all of them having something other than 0, this one is definitely more stable, because there are some, including the central atom here, where we have a double bond to oxygen and a single bond, single bond, single bond, and all of those with single bonds then end up taking on the extra electron that we have the -3 from. So this is actually the more stable configuration because of the fact that we have two formal charges of the atoms that are 0, which means the whole thing tends to be a little bit more stable because of that. But the whole idea of this is that phosphorus has 2, 4, 6, 8, 10 electrons. And some can even have up to 12 electrons. That's where SF6 comes from. That's definitely a situation where we have an expanded octet. Now, instead of sulfur having 2 pairs like this and then 2 singles, then sulfur ends up doing something that looks like this, where each one of them can then bond with a fluorine atom. And that's where SF6 comes from, and that's also an expanded octet, but that's as high as it goes. 12 is the highest number. So more than 8 electrons, here's, it just talks more about this eliminates the charge on the phosphorus and the charge on one of the oxygens. So the lesson is when the central atom is in the 3rd row or below, expanded octets eliminate some formal charges, like some formal charge issues. So this one actually is the more stable of the 2. So covalent bond strengths, this gets pretty simple. We have how much energy does it take to break this bond in half and to form 2 atoms of chlorine instead of having the 2 atoms bonded together to form a molecule. This is called bond enthalpy. Bond enthalpy is about the amount of heat it takes to break a bond. When we form a bond, it gives off heat, and if we break a bond, it absorbs heat. Okay, so that's good to know for that. So here's a whole list of single bonds and multiple bonds, meaning double bonds and triple bonds. And there are no quadruple bonds. That just doesn't happen. So the table lists the average bond enthalpy for many different types of bonds. Average bond enthalpies are positive because bond breaking is an endothermic process, or the bond breaking means you absorb heat or energy. Okay? These average bond enthalpies, The CH bond in methane will be a bit different than the CH bond in chloroform because of the rest of the stuff that's there. That changes the electronegativities of the strength of the bonds, but only slightly. It doesn't change it that much, I don't think. That's something to remember, but not focus on too much. So enthalpies of reactions, this is something we talked about in the beginning of Chapter 8 when you saw sodium and chlorine go from their elemental states into sodium chloride, the lattice. So this is something that we've already taken a quick look at, where bond enthalpies, when we're breaking bonds and forming bonds, how it changes the energy of the system. I don't really need to say much more than that, other than what we do is we take a look at all of the bonds that are broken, and we add them all up, and then we subtract them from all the bonds that are formed. And that's how we get bond enthalpy, or delta H of the reaction. And I'll show you some examples later on with that. Here's one example, but in the problem sets we're going to do a couple examples. So here we got CH4 and Cl2, and then we break one of the CH bonds to throw in a CCl bond. And then you see over here we're forming an HCl bond. Okay, so that happens, obviously, it just explained it. One CH bond and one I forgot. So you got to keep count of everything. We're breaking a Cl-Cl bond, and then we're forming a CCl bond, and an HCl bond are formed. And then we take a look at the difference. This right here is when we add up the bonds broken and we subtract them from the bonds formed, and then we get the difference in the heat of the system. And we'll go over examples of that. Okay, enthalpies of reaction. This looks way more confusing than it actually is, and I will go over specifically how you do this in the actual screencast for the problems 8b. Okay, if you have, like, there's a clear bonds, double bonds take way more. Obviously, double bonds, if you've seen me do the models, like a double bond is smaller in length, but takes more energy to break. A triple bond is even shorter and takes even more energy to break. And that's it. Okay?